So what we're doing now is forces. And let's recall, I think, kind of the main issue. One is you want to keep your forces separate from your accelerations. The main thing we'll be focusing on this situation, in this section, is cases where A is 0, A is constant, and you're given it, or the A is given by centripetal acceleration because you're moving in a circle. Now on the force side, we're mostly going to focus on tension, pushing and pulling, weight, and then our two contact forces, normal forces and friction. There is one force that we will deal with in the class that's not in this list that I gave you yesterday, because we deal with it in a later chapter when we do energy, and that is the force due to a spring. So just keep that in mind, that down the road you will have to add this additional force to your list. What we are going to focus on today are problems that involve this. And essentially every problem will always have some of these. For instance, weight will almost always be there because we very rarely do anything in outer space. But the conceptual challenge is dealing with friction. So that is today. And what we will focus on Friday is how to handle centripetal acceleration. And the conceptual challenge that we'll be dealing with in all of these problems is the fact that there's almost always going to be some sort of inequality that we're going to have to know when to treat as an equality. And what do I mean by that? I mean that we're going to be dealing with things like maximum, minimum, and just to. So maximum to move, minimum to move, maximum to not move, minimum to not move. We're just going to start moving. These are the phrases we're going to be using to figure out what to set equal, usually to 0, but not always. And in learning how to deal with these phrases and the physics of the situation is what we'll be working up to. The final piece in all of this is that we almost always have to deal with components. And the twist we're adding now is we really want to choose a smart coordinate system. So that is kind of the overview of the problems we'll be dealing with this week. Any questions? Now, before we start on the problems, I have a couple demonstrations we'll be doing first. I don't really have any clicker questions with them this time. I just want to show you some of the behavior that's associated with friction and the concept of just moving that will be important in doing these problems. So the idea we're going to be highlighting in these demonstrations is the following: that the force of friction has two pieces. One, which is static friction, which has this feature that it can change in size. It's given by a less than or equal to. And the other is kinetic friction. Now, in all these cases, we have a coefficient of friction that you will be either given or have to solve for. But those are the main relations we're going to be looking at. And how does it basically work? So we have our handy dandy little boats, okay? And we have our people. Actually, think of these as cars, I guess, cars or carts. and they're on a surface, and we're going to pull them. And the question is, how much force does it take to pull them along? So the mass of these is 5 kilograms each, so it's 10 kilograms total, right? So the weight of these is that times gravity, mg. So we've got basically 100 newtons sitting in here. Now, we're going to try and pull them, and you can see on my scale here the force required to pull them. And right now I'm pulling with 10 newtons, and they're not moving at all. I'm pulling with 5 newtons now, and they're not moving. I can go up to 15, and they're not moving. I can even go up to 20, and they won't move. So there's lots of forces I can pull with, and they won't move. If I pull a little more than 20, they start moving. And it's really hard to see, but if you watch it, I get a little bit above 20. Oh, that one, oh, I'm pulling up at an angle now. And then it drops once it starts to move. Now, it will be a little more obvious. This one is a smooth cart. The other one, the next one I'm going to use here, has sandpaper under it. So now notice I'm getting all the way up to 30, 35. Now the cart's moving, 40, 50, 60, and then it moved. And notice how much it's jumping down once it slides. It goes all the way up to 70 and jumps down to 55 when it slides. So what is happening here? Anyone have an idea of what we were demonstrating with this demo? So I had an object on a table, and I'm pulling it. Yeah?
The static friction is higher than the kinetic friction, so once it's overcome, it goes back to the kinetic.
So the jump down is the static friction ends up being higher. The maximum static friction is higher than the kinetic friction. Why was it not moving until I reached some key level? Well, what I want you to do, here's my block. I already drew it there. I'm drawing it again. Let me draw just the block. I want you to make a free body diagram for this block that I just pulled on. Make a free body diagram in your notes. And then I lied. We will have a clicker question. And then tell me how many forces you end up with in your free body diagram. Excellent. Almost all of you got 4. I'll be curious to see what you're missing if you have 3. What are the 4 in this particular problem? Anyone want to give me some? Yes?
Force of friction.
We have a force of friction. I'm going to use this diagram, so my force of friction is going backwards. What else do we have? The normal force. That goes up. What else do we have? Gravity and the pull. Gravity and the pull. So people who answered 3, just out of curiosity, shout out which force you were missing. Most people were missing normal. Interesting. A few said friction. Remember, any 2 objects in contact, there's always the normal force. That's always there. Now, this is a fairly straightforward one. We make an x and y coordinate system, and we look at each direction separately. And in this case, for the y direction, there's one case we know a is 0. It doesn't accelerate up or down because it never gets any vertical velocity. So ay is 0. So F normal minus Fw equals 0. So I know my normal force is mg because I plug in here for Fw. Now, what the whole demo is about was if I look in the x direction, and initially Ax is 0. So what that tells me is F pulling minus Ff has to equal 0. So my pulling force has to equal my force of friction, which I know is less than or equal to mu s times Fn, which is not changing. And that is this whole piece of the beginning part, where I start with some very small pulling. I do not accelerate at all because the force of friction is allowed to cancel it. And that is the key thing here. This force of friction is able to cancel out whatever pulling I apply until I reach my maximum. Then it moves. And once it moves, whether I am accelerating or have constant velocity, I now have to use kinetic friction. And in this case, it starts to move with velocity in the x direction that's constant once it's moving. So I still have an ax equals 0, but for a different reason. It's now moving at some constant speed. Now my Fp minus Ff still equals 0. Fp equals my force of friction, but now it's kinetic friction. And so it's equal to mu k Fn. And the general rule is that mu k is almost always less than mu s. And you all know this from your everyday experience. If you push on anything, right, once you get it going, it's easier to keep it going than it usually is to get it started. And that's just a consequence of kinetic friction is almost always less than static friction. So if you have to move a device or an object, once you get it moving, it's easier to keep it moving. That is our first sense in which we see something changing and then you reach a limit. Any questions on that? Yes?
Should we be familiar with an object's momentum at all?
So momentum is something we will talk about in the context of forces in a later chapter. So you don't need it for this. If you think in those terms and it helps you to figure out what's going on, that's fine. Other questions? So now let's see it in another context. Okay? A common thing to have is a ramp. So I said we're building up the pieces, and often things are moving at an angle. Why? Because we like to ski, we like to snowboard, we like to jump motorcycles, we like to jump bikes, we drive on hills. Any other sort of, we like to build pyramids if we're ancient Egyptians. So, almost anything we do, often a ramp comes in. And one of the things to keep in mind, which we'll really get into more detail later, and we should have said at the beginning, is when it comes to forces, acceleration, velocity, most objects, people, cars, bikes, roller skaters, arrows, bullets, baseballs, footballs, all of these objects we can treat as a small little block, what we call a point particle. So when we do all these boring problems with blocks on inclined planes and ramps, they look like they have no connection to reality because unless you're still a little kid, you're not really sliding blocks tying down an inclined plane. I heard a great story, when a 3-year-old is throwing all their toys down the stairs, the parent is thinking, why are you trying to break all your toys? And the kid's looking, wow, they all fall. No matter which one I throw, it falls. They all fall the same. And that's what we want to develop here. Everything acts the same, and so we can just treat it all like a block. And anything that's at an angle is a ramp. So what happens, right, is you start to tilt your ramp, and notice it doesn't move. Think about, because we'll ask the question when we do the problem, how many forces are acting on it? Why is it not moving? It's not accelerating, it's not accelerating, it's not accelerating. And then at some key point, it goes. So it has an acceleration, and it slides down the ramp. And so that is the other type of, notice, a just to move problem. There was a maximum angle at which it would not slide. And in all of these cases, it's that same math problem, right? If we're looking for the maximum angle to not slide, what are we going to be doing? We're going to be using the fact that static friction is a changing force and find the case where force of static friction is equal to this. Because if we make it any bigger, static friction can't get any bigger, and now it will slide. So we solve for the point just before anything happens, which means two things. In this case, we're both using an acceleration that's still 0, even though it's about to have an acceleration, and we're taking the maximum of that to find the place where that's just about to change from not being 0. Now, one thing I can do, right, is, again, this is the one with sandpaper, so it's got a higher coefficient of friction. So I can get to a much higher angle. And it tends to tip over. Let's see if I can get it. Actually, you know what? Let's see if I cheat and put the mass like that. I can get to a much higher angle before it starts to slide. Okay, there, it just went. And it made me nervous. But notice that is because mu s is much bigger. So the maximum force of friction is much bigger. So this can counteract bigger and bigger forces. And we'll see that in the problems we do. Any questions on that? Now keep in mind, there are lots and lots of infinite, as I said Monday, variations in which something like this can come in. We're doing inclined planes today. It could be a ladder against a wall. When is the ladder going to slide? It can be you and your friends building a pyramid, and when is something going to slide off? So there's lots of ways this force of friction can come into things, but it's all the same basic concept, and you'll use the same techniques. The math and algebra will be slightly different from problem to problem. So let's go to our first problem. No, that's our first clicker question. There we go. This is the standard. Block resting on an inclined plane forms an angle of 30 degrees with the horizontal. What force is required to hold? Yeah. What force is required to hold the block in place? We're also going to talk about what force is required to accelerate the block, and we're going to do it with and without friction. Now, this would never be an exam problem like this, because this is actually 4 problems. I'm lazy. I just want to type it 4 times. Right? So this is 4 different problems in here. But it gives me a chance to do all 4 of them, because they're all basically exactly the same problem. What we just use are different facts and information about force of friction. So force of friction, these 2 equations with force of friction, is something you have to become very comfortable with. Now, the other thing you have to become very comfortable with in physics is choosing your coordinate system. So we're going to start this problem. Before I even do the problem, let's draw the picture for the problem. Now, one thing you may have noticed, were there any numbers given to you in this problem? Which one? I gave an acceleration. I also gave an angle. I didn't give you anything else. I didn't give you a mass. I didn't give you other stuff. So there is I didn't give you coefficients of friction when we do the friction part. I'm going to do this problem all in variables, just so you can see the structure of it and not plug in numbers. And in most of the force problems, it really is a great advantage to you if you only plug in numbers at the end. Because one of the things that often happens, for instance, I'll just notice here, mass, not always, but often cancels, right? Because you've got an mg for gravity, and you've got an ma in the second law. So a lot of times, if you don't get comfortable doing it with variables and noticing when ones cancel out, you will not realize that you actually have enough information. So the problem might not give you the mass, and it might want a number for an answer, and you're like, I need the mass, I need the mass. That's because you're used to plugging it in early on. If you do the algebra, you'll see it cancels. So with force problems, I really encourage you to do it the way I'm going to do the examples in class. I'm going to keep it all variables, and then you get used to that. So that's point number 1. Point number 2 is we're always going to be looking at our components. Now, occasionally, only one of the 2 directions will matter. So we won't need to use both components. But everything's almost always going to be 2D. And the question is, how do we draw our coordinate system? And you have often more than one choice. So for instance here, I can draw a coordinate system with an x and a y axis like that. Notice what I've done is my x-axis is parallel to the ramp. And I could also draw a normal x and y axis. Here, the key aspect of this is the y-axis is parallel to gravity. So if I just look at kind of the three basic forces that I would be drawing for this block, let's not think about the problem right now. Let's just think about a block sitting on the ramp, no friction. I would have weight down. Notice the normal force is always perpendicular to the surface, so it's off at an angle. And those are my two main forces. Notice in my two coordinate systems, one of these has to be broken into components. If I use this coordinate system, weight is already in the y direction because it was parallel to gravity, and the normal force will have two components. If I use this coordinate system, then gravity gets broken into two components. The normal force is already in the y direction. So depending on what's going on in the problem, one of these two coordinate systems will be easier to use. Roughly 80% of the time you will find myself and the TAs using this coordinate system. Why do we mostly use this coordinate system? Because most of the time, if I look at the acceleration in this coordinate system, AY equals 0 and AX equals something. Maybe 0, maybe not. But we very rarely have the block coming off the ramp. In this coordinate system, AX and AY will both have to be broken into components if A is along the ramp. And it just turns out it's easier and usually nicer to deal with the acceleration only in one direction and know that it's always 0 in another than to have the two accelerations. So this is the common coordinate system we'll use. What that means is you will have to most often break weight into components. And you want to be very comfortable drawing your triangles. So here is the direction of the weight. Here is my angle theta. Here, actually let me put the label for weight down here. If I look at it, right, if I'm making an x and y coordinate system like this, here's the two components I need. So I need to know this angle in here is 90 minus theta, because weight makes a right angle. That's a right angle. So the angle in here is now theta. And so this becomes FW cosine theta, and this becomes FW sine theta. Again, trig and geometry are the key. And this is the one breaking into component step. I really suggest three choices for this because it comes up all the time. One might be to memorize it. Two might be to have great faith in your ability to always do the geometry. And the third is to keep in mind an important trick. If a ramp has an angle of 0, which direction is gravity? Straight down. So, and which direction is the x-axis if my angle is 0? Horizontal. Which of these disappears when theta is 0? The sine of 0 is 0. This is what we call in physics about sort of checking our answer. Does it make sense? If I make a component parallel to my ramp, along my ramp, it better be 0 if my ramp angle is 0. And sine is 0 at 0. Cosine is not. It's 1. So you can always, when you write it down, use that sort of mathematical idea to check it. So those are 3 things. Okay, you can kind of memorize what's going on. You can use your geometry, or you can use that intuition. If you memorize, know that the formula has to do with that angle. Every now and then, that's not the angle you're given. So you got to worry about that just a little bit. Any questions on that?
Yes.
Ah, there. Yes.
So when you were saying that the component, like, so those components for FW is the one, like F to be cosine theta and F to be sine theta.
Right.
F to be 0 then?
No, what I'm saying is, if my ramp was completely flat,
Yeah.
not at some angle, so theta 0, then this one has to disappear. Because when I'm on a flat ground like this, gravity's only going down, not along the ramp. Or let me actually do it on my ramp. Right? When the ramp is 0, gravity's all perpendicular to the ramp. It's only when I have an angle that gravity has a component along the ramp and perpendicular to the ramp. So that's how you know which one of these will disappear. The normal force is always perpendicular to the surface. So the angle, if I use a mass, right, the mass is sticking up perpendicular, right, so it's easy to see. The normal force is always parallel to this mass. So right now it's straight up. Right now it's at this angle. And so if my coordinate system is perpendicular to the surface and parallel to the surface, the normal force will be in my y direction. And we'll see that in the problem that we solve. Now, if I pick a coordinate system that's just my normal x and y, then gravity is always in the y direction, and the normal force picks up components, because it's now at an angle. So the normal force would have a component in the x and y direction. And this is where the language gets a little confusing, because whether I pick my coordinate system at this angle or at this angle, I still call them x and y. And that language is a little confusing. So what is my x and y component? First, I have to pick my coordinate system. Then I get to decide, if I pick this coordinate system, notice my normal force has components. If I pick this coordinate system, then it's gravity that has components. You'll see it as we do a lot of examples and as you practice them. And luckily, the one for discussion section, you get to practice, because there's a ramp. Now, any more questions? Notice, I did say at the beginning, we're still only using basically one concept, F equals ma, with the components. But it is getting much deeper. There's a lot more to that concept. So I agree, it is kind of harder now. So let's go back to our question. What force is required to just hold the block in place? And in this case, we're going to ignore friction. We'll do that one first. So we go to our clicker question and always ask ourselves, how many forces are in our free body diagram? So we're going to have a block on our inclined plane. It's at some angle. There's no friction. This has friction, so it's staying on its own. But if there's no friction, it would be sliding down. So I have to hold it in place. And the question you're asking is, what force is required to hold it in place? What? Oh, I didn't start the question. Wait. Oh, yeah, I used this same one for every one of these. I just made one slide. I'm being very lazy today. One slide for all 4 questions, one slide for all the clicker questions. When I post the lecture, we'll try and make it clear how many were in each one. The first one had 4. Let's see what we got. Excellent. 56% of us went with 3. That's a very good start. And I'll tell you right now, in some ways, if you miss that question, the rest of the problem becomes impossible. So these are just ones. You've got to get that question right. So we've got our block. It's sitting in our inclined plane. Our free body diagram is weight down, normal force perpendicular to the plane, and our force of pulling holding it in place, because gravity is going to pull it down. Now, notice I drew my free body diagram with all the forces coming from the center. That is not unique. You can also draw it this way. You know, sometimes, because that's where the force pulling is, it's pushing up on it. That helps. I also like to draw a block. A lot of people, like if you notice on the Mastering Physics, they'll just have a dot that you draw the forces from. And in the Mastering Physics, they're really looking at it. This version is what they'd like you to draw. Now, we want it to be just in place. We have to pick our coordinate system. We know, therefore, that our acceleration is going to be 0. So in some sense, for our acceleration vector, it won't matter which one we do, per se. But what we do know is if it accelerates at all, the acceleration is along the surface. So because of that, I'm going to pick an x and a y parallel to my surface. And you need to draw this. If you're doing the problem, you need to draw your free body diagram. And you do not draw your acceleration on your free body diagram. It is not a force. It is the acceleration. But you should indicate somewhere to yourself, so you don't forget, what the acceleration is. So these are the 3 pieces that you need. And then, once you have this picture, you can just go and write down your equations in the 2 directions. In this case, we will have to break gravity into our 2 components. So we will have Fw cosine theta there, and Fw, sine theta there. And in our y direction, y is positive up, so the normal is positive. The Fw cosine theta is negative. It equals ma sub y, but a sub y is 0. In the x direction, our pushing is positive. We have a minus Fw sine theta equals max. And we want to know when that's going to be 0. So we see that the force we need to push with is just the weight sine theta, which would be mg sine theta. So we would need to know the mass and the angle. We were given the 30. If I wanted a number here, I would need to know the mass. So that is the minimum, or the force I should push with just to hold it in place. Notice, by breaking it into components, I immediately see from my x direction that Fp minus Fw sine theta equals max. So if Fp is greater than Fw sine theta, then ax is greater than 0, and I accelerate up the ramp. If Fp is less than Fw sine theta, then ax is less than 0, and I go down the ramp. So unlike the case of friction, it's not like there's a range of pushing I can use and it won't move. And there's a maximum value that keeps it in place. With no friction, it accelerates either up the ramp or down the ramp unless I hold it with exactly the right force. Once I'm holding it with exactly the right force, then it just stays there with no acceleration. If it's a little less, gravity wins and it slides down. If it's a little bit more, I win and I push it up. So I can use this right away to answer the second question: how much must pushing be for A to be the 0.5 meters per second squared. Right? So if I want to do the second part of the question, I just plug in A equals 0.5 meters per second squared, and I can solve for FP. That's the other advantage of leaving it as variables to the end. If the question does happen to ask two different things, you don't have to resolve it. You can just plug in your numbers. You're done. Right? We've solved the general problem, and now we can just plug in whatever numbers. If I ask you for a different mass, what do I have to do? You just plug in for that mass. So any questions on the non-friction case? Yes?
Can you explain how FW sine theta equals mg sine theta?
Oh, remember that the weight is one of the forces we have a formula for. The weight is always given by mg. So I'm just plugging in for the weight here. Yep, good question. And I could do that right here as well. I just haven't bothered to do it. Other questions? Excellent. So now we're going to ask the question, same question, but with friction. So we ask our clicker question, how many forces are acting on the block now? And this one will be very quick. I'm just going to give you like 30 seconds. How many forces are acting on the block where now we're doing exactly this problem? I'm going to be pushing on it, and there's friction. How much do I have to push on it so it doesn't slide? But there's friction and me pushing and the block and the angle. Excellent. 4. We've just added friction, so it was 3 before. Now it's 4. Now, here's the harder question. What direction does friction act? So let me remind you. I'll draw the picture here. Right? We have an inclined plane. We have a block on it. We're going to push with some necessary force so that the block does not slide. Which direction is friction acting? Most of you went with down the plane. That is incorrect. Now, let me ask you this. Let's suppose I'd ask the question, which direction is friction acting now? Answer that one real quickly. Not as much confidence, but now A is correct. Most of you switched to the right answer. And here is what's going on. And here's what makes it challenging. There's 2 moments at which I'm not going to move. The first question I am asking, right, is what force is required to hold the block in place? We're holding the block in place. Whoops. So if that's what I'm doing, I'm trying to hold the block in place, then the block is attempting to move down. And friction always opposes that attempt to move. So friction will be up, and it helps me. That means I need less force to hold it in place. In fact, I might need 0 force to hold it in place. How much force do I need to hold that block in place so it doesn't slide? 0. It's just sitting there. It's not sliding. Friction is doing all the work for me. If I put it up here, okay, I now need some force to hold it in place. But I need less force than if there was no friction, because friction is still helping me. If I want to push it up the ramp, now what's the attempted motion? Up the ramp. So now which direction is friction? Down. So if I try to push up, there's a new direction for friction. It goes down. So the way this works, if I look at my free body diagram, for the first case, I have that. Friction and pushing going up the ramp. Notice normal doesn't change, weight doesn't change. If I pick my x and y, the y direction is the same as before. That hasn't changed. We have a new x direction equation. What do we have? We have minus Fw sine theta. That's the component of the weight. And for this case, we have a positive pushing and a positive force of friction. And we're going to set that equal to max, which is 0. Now, that means the pushing force we need, the magnitude of it, is just Fd sine theta minus our force of friction. And the maximum value for this will set the minimum value for this. And how do we get the maximum value for the force of friction? This is the static friction case. We use the equal sign here and make the force of friction equal to mu s Fn, which we solved using our y direction equation. And that is the central feature of all of these problems. And so I'm just going to give you the answer now, and I'm going to post a more detailed solution for you. So from the y direction, we will get that the normal force is mg cosine theta. From the x direction, we have it already up there, and we plug in. So the pulling force is mg sine theta minus mu s mg cosine theta. Now, one last point. The question asks us, what do we do? What force is required to accelerate it at our 0.3 meters per second squared? Then this equation changes, right? The direction of Fk is now up. I'm sorry, is now down. And so we change the minus sign here, and we will have an Fp equal to mg sine theta plus mu k mg cosine theta. So what I'm going to post for you is the details of this last bit, and then the second problem that's listed as a lecture problem, I will probably post just as a Camtasia capture video. And tomorrow in class, you're going to practice these more in discussion section. And then on Friday, we do circular motion.